Practical Web Application Firewall bypasses. Just a quick preface to this presentation. All of the techniques we're presenting have been used to bypass some WAF at some point in time. Of course, not every WAF is the same, but hopefully you'll find some of these techniques useful in the future. First, a brief introduction. My name is Robert. I'm also known as Not the Ghost on HackerOne. I'm a 17-year-old high schooler at Interlake High School in Washington State. In my spare time, I enjoy doing CTFs with the Redpwn, hunting for bugs on HackerOne, and just messing around with random projects.
I'm Philip, and I'm known as Kinkoid on HackerOne. I'm a 16-year-old high schooler who does CTFs with the Redpwn and hunts for bugs on HackerOne.
Let's look at some background information. For those who are unfamiliar, a web application firewall, also known as a WAF, is an external application designed to filter out attacks. These generally operate on layer 7 over HTTP traffic, hence the web application part of web application firewall. These tend to be more common when pen testing larger companies. For example, some DoD websites are protected by a generic WAF. At the same time, it's important to keep in mind that there's a security usability trade-off. So what that means is WAFs that stop more attacks also tend to generate more false positives. For example, here we have a proprietary WAF which manages to stop 100% of attacks. Unfortunately, it also has a 100% false positive rate. But on a more serious note, this security usability trade-off is generally beneficial for pen testers because companies tend to err on the side of usability when designing WAFs. These WAFs can be designed to prevent a wide variety of attacks. Oftentimes this could include SQL injection, cross-site scripting, and local file inclusion, just to name a few. In this presentation, we'll be focusing on XSS or cross-site scripting vulnerabilities specifically for a couple reasons. For one, JavaScript and HTML syntax is a lot more fluid. In comparison, SQL has a lot less statements and is a lot more rigid. Also, HTML and JavaScript have a lot of stuff to exploit. There's tons of random global variables, some not very well-known behavior, and random undocumented features. Also, XSS is arguably more relevant. You'll probably find more reflected XSS vulnerabilities than SQL injections.
In general, most companies use a very small number of common WAFs such as Imperva, F5, Cloudflare, and Akamai. Most of these WAFs can be easily bypassed to achieve XSS using some common strategies which we will explore today. At its core, most if not all WAFs use regular expressions to filter out malicious payloads. For example, this regular expression taken from the Cloudflare blog provides some insight into how WAFs operate. This has the advantage of providing a very fast and simple mechanism to filter out requests. Keep in mind that WAFs operate over every single piece of network traffic. Any latency in the WAF would be felt across every endpoint. WAFs need to optimize for performance. They need to decide whether to block a request very quickly. While JavaScript execution might allow for a more comprehensive solution, most WAFs can't afford the overhead. Some of the more common filters we've encountered include blocking function calls, blocking keywords like onload and inner HTML, and blocking special characters such as array index operations. In general, highly complex operations like creating objects and function calls tend to have a higher chance of being blocked.
Another useful strategy that WAFs employ is the execution context. So this looks at where the payload is actually running. For example, an injection that is inside JS code could probably be handled very differently from a plain HTML injection. Similarly, if we're injecting inside an attribute, for example, of an input element, that would also require a different payload to escape. By taking into account the execution context, we can greatly reduce the number of false positives. At the same time, this also increases the complexity of the WAF because it requires it to have some understanding of where the payload is being executed. Such a feature tends to appear more commonly in reflected access scenarios, but overall, this isn't too common, at least from our experience. One crucial part of exploitation is payload construction. So this attempts to answer the question, how can I get an arbitrary value into a JS variable? One thing to note is that payload construction in and of itself isn't a bypass necessarily, but it is a crucial part of later execution. For example, oftentimes we'll want to construct an XSS payload, but the WAF will filter for the SVG onload string literal. There's two general categories of payload construction. First is string construction, and this relies on the idea that WAFs operate on the literal character content of payloads. Luckily, JS code is quite complex, so instead of embedding our payload string directly in the code, we can construct it gradually through JS code. It would be infeasible for a WAF to fully parse and execute the JavaScript code, allowing us to bypass the WAF, hiding our payload. Another more arguably gimmicky technique involves string hiding, which exploits browser features to hide payloads in weird places. The crucial idea here is that JS or JavaScript has access to a wide range of data, much of which isn't actually sent to the web server. And we'll go over this more in depth later. Perhaps the most basic example of string construction is JavaScript parameter splitting. The idea is we can split a payload across multiple variables and iteratively construct it. One interesting thing to note here is that the bottom example actually involves constructing the payload from right to left. So some WAFs will filter out sequences. For example, they'll block parentheses after SVG onload appears. Constructing the payload from right to left can bypass these regex filters. Another example is DOM parameter splitting, where we split the payload across multiple HTML elements and then reconstruct it in one final step. This particular scenario assumes an HTML injection, but it can also work with, say, an attribute injection after we escape the attribute. One useful trick that we use in this technique and also later techniques is referencing elements by their ID. This allows us to avoid more complicated functions like, say, document.getElement by ID, and gives us an easy way to access our injected HTML elements. Dataset parameter splitting is very similar to DOM parameter splitting, except for it only involves one element, which can be more useful in certain scenarios where WAFs will filter out multiple HTML elements. In this case, we split the payload across multiple dataset properties, and then we combine them at the very end in the onload. We can also abuse the fact that the inner text property only looks at the text content of the element. So by interspersing arbitrary HTML elements, we can actually split the payload. We can also HTML encode entities to further obfuscate our payload. Window.name payload storage is pretty interesting. It abuses the fact that window.name is preserved across redirects. In other words, if we assign to the value of window.name and then trigger a navigation, even if it's to a cross-origin domain, window.name stays the same, which means that we can use this to store arbitrary contents, including, for example, an XSS payload.
After constructing or hiding the payload somewhere, we need to use a browser API in order to execute it somehow. There's two general paths we go about for payload execution, eventually allowing us to perform something interesting. First, we can execute user-visible code. The end goal is usually to create some sort of visual indicator, for example, an alert box, which is enough to demonstrate XSS to a triage team. Alternatively, we can attempt session exfiltration, generally by extracting a session cookie. Note that this is somewhat limited, failing against targets which have HTTP-only session cookies. In order to exfiltrate data, we need to somehow make a network request. To do that, we can redirect the user back to an attacker-owned server. The easiest way to achieve code execution is by simply assigning to inner HTML and outer HTML. If the strings inner HTML and outer HTML are blocked, we can construct the string by appending other strings either inline, as shown here, or as previously documented in the payload construction section. The easiest way to exfiltrate data is through location setting, redirecting the user to an attacker-controlled server. By appending document.cookie to the end of our URL, we are able to exfiltrate the session cookie. In an actual attack scenario, the attacker could then redirect back to the vulnerable site to avoid arousing suspicions. One very big advantage of this method is that it avoids the need for any function calls which tend to get processed more strictly. In general, location assignment can often be the sink for other methods. This method also works regardless of CSP as long as you can achieve code execution, which isn't necessarily true for some of the later methods. The primary disadvantage is that this won't work for applications with HTTP-only session cookies. Regardless, cookie exfiltration is usually good enough to demonstrate impact. Certain WAFs will block direct assignment to special variables like location. However, there are some pretty clever ways to bypass this filter. For one, you can insert arbitrary comments between location and the assignment operator. Alternatively, you can abuse a lack of semicolons to place the rest of an assignment expression after a new line. Another way is by using the plus equals operator. To do this, we first use the plus equals operator to assign to the hash. This doesn't trigger a redirect, which allows us to safely store our exfiltrated data. Note that the hash defaults to an empty string, so on a page with no hash, the hash just becomes the user's cookies. Next, we can use the plus equals operator to assign to location.host to actually trigger the redirect. The attacker could use wildcard DNS or register the specific subdomain to then host a page which steals cookies. This exploit is a bit more involved, so we'll be doing a brief demo.
On the right here, we have a web page that is vulnerable to XSS, a simulated web page, the payload parameter here. As you can see, we've injected an H1 element with injection. And on the left here, we have a request bin, which allows us to easily see and log any requests that hit it. So, for example, if we take this endpoint and we open it up, we'll see that there have been the requests and they get logged on the side here, which is very useful for testing information exfiltration. So if we go over here, we can create a few cookies. Now we can see that the document.cookie value gets populated. So now we're going to try to exfiltrate this cookie, which could be, for example, a session cookie or any other useful information that an attacker would want to steal. So the easiest way would be just assignment to location. So we can do that by assigning to location and then concatenating with the value of document.cookie. And if you see we do this and we press enter, we'll see that the value of document.cookie gets logged here on the side because it gets concatenated into the path. That's one way to do it. Unfortunately, many WAFs actually block direct assignment to location. It's a pretty well-known trick at this point. To get around this, there's a variety of ways there's a variety of tricks. For one, we can try inserting junk between the location and the equals sign. So for example, if we have a cookie here, if we have a comment here, this is still valid JavaScript code, and running it would still trigger the redirect, but it looks a bit different to the WAF, so it might confuse it. We could also do this with, say, for example, a line comment, so 2 slashes, and again, this would work. One interesting thing is HTML comments actually also work in JavaScript. So if we do less than, exclamation, and 2 dashes, this operates in the same way as a double slash comment. but some WAFs don't properly parse this, so this would be a bypass for some web application firewalls. A slightly more complicated technique involves using the plus equals operator. So to do this, we first use the plus equals operator with location.hash. And we do this because we want a place to put document.cookie, which does not trigger a redirect. If you see, if we evaluate this statement, the document.hash gets populated, but since it's a hash change, the document doesn't, the page doesn't redirect to anything else. In essence, what this is doing is location.hash is equal to location.hash plus document.cookie. But initially, location.hash, when there's no hash, is equal to an empty string. So, for example, if I just open up a random page and then I type in location.hash, we'll see that it's an empty string. So when we use the plus equals operator, in essence, it's just assignment to location.hash, but it's like a bit obfuscated. And then in order to actually trigger a redirect, we can use location.origin plus equals, and then we do .attacker.com. So what this does is it changes the origin. Location.host, sorry. Yeah, location.origin for some reason doesn't work, even though it looks very similar. Location.origin and location.host look very similar, but we need to do it with location.host. So what this does is it redirects the page to the current document origin, which was xss.gink.workers.dev, and then we append .attacker.com to this origin. But since this top part is controlled, this attacker.com is controlled by an attacker, we can just easily register this xss.gink.workers.dev as a subdomain, or we can use a wildcard subdomain here. And then we can serve a page which would then read the location.hash, because I don't think we can read it here, but if this was a valid page, we would be able to read location.hash. And then it could like send off the cookie to an attacker-controlled server.
If assignment to location is blocked, images can also make requests to external servers. One caveat here is that these requests might be blocked by the content security policy. There are a couple of ways to go around doing this. The simplest way would be to create a new DOM image object and assign a source attribute to it. Unfortunately, assignment to source tends to get blocked. One bypass is by using the source set property. Unfortunately, due to how source set is parsed, spaces have special semantic meaning. This means that assigning directly from document.cookie, which normally contains spaces in it, won't work. In order to get around this, we first assign to low source. Although this property is deprecated, it still functions similar to source in that it will automatically URI encode its contents. Assignment to low source thus allows us to mutate the string representation of the cookie, URI encoding it without any function calls. We can then extract it normally with assignment to source set. We'll also be doing a brief demo for this exploit.
So first, let's modify our payload here to create a generic image element with IDA. And you can see if we go into inspect element here that the image element does get created. Now we can simulate the addition of cookies by setting a few cookies. And we can see that document.cookie gets populated. Now let's try to exfiltrate these values. First, the most generic way would be through src. So if we just do a.src, and then we assign to the value of our endpoint and concatenate it with document.cookie, we can see that we log a request with the two cookies exfiltrated. However, if we try and refresh the page, and we try to do the same thing with src set, we'll note that it actually doesn't work the same and it will fail. So if we do it this time, the only difference here is we're using src set instead of src. That's because src set works by having an image candidate string and then a pixel size. So it has two values actually, which are space separated. So what it's trying to do is trying to parse the first cookie as the image URL, but then it's trying to parse the second value or the second cookie as a candidate size. But obviously b equals 2 isn't a valid attribute, so it says it errors with an unknown descriptor. So in order to get around this, we have to first encode the value, encode the entire cookie to get rid of the space here, which is causing errors. So to do that, we can assign to low SRC first. And this is pretty interesting. After we assign to low SRC, if we look at the value of low SRC in the console, we'll find that it's actually mutated. So it became URI encoded and it has the current location appended to it. So if we were to assign to SRC set now, and this time instead of concatenating with document.cookie, we want to concatenate with low SRC. And if we do that, we'll see that we do get a result. And looking at the logs here, we see that the path has the two cookies we want to exfiltrate appended to the end. So this demonstrates, it's a slightly more complicated exploit, but it's pretty cool how we can use low SRC to mutate the value of document.cookie, URI encoding it, which then makes it a valid attribute to concatenate with our endpoint for SRC set.
We previously mentioned that WAFs tend to use regex to filter out payloads. This means their filters will block payloads or become more suspicious if certain payloads are contained in order. However, payloads are traditionally constructed from left to right. We can violate this assumption through right-to-left execution to bypass many WAFs and achieve JavaScript execution. One way to do this is with nested elements, such as the SVG shown here. For nested HTML elements, the children's load handlers are executed first, and the event bubbles up to parent elements. Thus, in the example of nested SVG elements, the innermost load handler at the right is executed first, and the outermost handler at the left is executed last. Another way to achieve right-to-left execution is with loops. The while loop above uses the ternary operator to execute different code on subsequent loop iterations, executing the right part first and then the left.
Here again, we have a generic XSS vulnerability where the payload parameter gets reflected into the body of the response. So here, if we insert a SVG element, the IDA, we'll see that it does indeed get written into the body here. Now what happens if we have two SVG elements? We'll see that the rightmost one over here actually gets nested inside our first SVG element. That's because we don't have a closing tag for this SVG. So it assumes that the next element is just a child. It becomes more interesting when we try to assign onload handlers, because in HTML, the innermost or the child's onload handler actually gets executed first. So if we have two different alert values here, on the child we're going to alert B, and on the parent we're going to alert A. We'll see that the B actually gets alerted first, and then A. So in other words, the code on the right-hand side gets executed before the code on the left-hand side. And we can do this to bypass some of the assumptions WAFs make about code execution, because usually they parse the code from left to right. So for example, if we assign some variable to document on the left-hand side here, then we can use this variable however we want. And usually this would bypass the filter because it would, for example, check for some keywords after the document keyword appears, but only to the right, not to the left.
Here are a few key takeaways from this presentation. In general, WAFs can never be perfect because of the large number of applications they protect and their ability to easily harm the user experience by blocking non-malicious payloads. As a result, the developers of WAFs will often allow limited JavaScript syntax, allowing them to be bypassed easily, especially by using obscure web platform functionality which bypasses WAF developer expectations.
Thanks for listening to our presentation. If you have any questions, we'll be in the HackerOne Discord. Alternatively, you can contact us with the emails on screen. Our presentation slides are also available at gnk.io/activitycon2020.